Hello dear students, this question is from GATE 2015 exam. It's from set 1 and is for 2 marks. So they have given you these two functions f and g and they're asking which one of these is functionally complete. Now you know the meaning of functional completeness. For example, NAND and NOR gates are functionally complete. That's the reason they are called universal gates, because every possible logic function could be implemented only using NAND gates or only using NOR gates. Similarly, multiplexer is also functionally complete. Now we need to determine which one of these two is functionally complete. So first method is using F, you try to implement NAND, that is NOT as well as AND. If you are able to implement NOT as well as AND using this function F, you can say F is also functionally complete because F derives NAND. Okay. Similarly, you can just derive NAND from G and declare it functionally complete. Okay, if you are able to derive it. Or you can also implement NOR. So first method says implement any gate out of NAND and NOR from the given function. But I don't prefer this method because it's kind of hit and trial. You'll just manipulate the inputs and sometimes you'll substitute 0 in place of some input and 1 in place of input. And you'll just try to derive these two gates, NOT or AND. That means you'll try to derive this pair or this pair. So there is no fixed procedure. In GATE exam, you might panic because at first place, you don't know if it is functionally complete or not. Okay. So best method is go with this one. If you are able to satisfy these 5 rules, you will say the given function is functionally complete. Okay. Let's try to solve this question using this method. It says, if any given function satisfies these 5 rules, it can simply be declared as functionally complete. First one is function must not preserve 0. Second one is function must not preserve 1. It must not be linear. It must not be monotone. It must not be self-dual function. What are these 5? Preserves 0. A function preserves 0 means on the input 0, 0, 0. If I input 0, 0, 0, output must be 0. In that case, we say it preserves 0. But the condition is it must not preserve 0. Okay. That means if on input 0, 0, 0, both the functions output are 1, only in that case we will say it does not preserve 0. Let's see the output of f in case of 0, 0, 0. See, y and z are 0, that means this entire term will become 0. Okay, x is 0, this term will also become 0. Y and z both are 0, so y complement dot z complement will be 1. 0 plus 0 plus 1. That means output will be 1 on 0, 0, 0. Now, if on all zeros output is 1, you can say it does not preserve 0. So f satisfies this property. Okay. On input 0, 0, 0, function outputs 1. Now let's check for g. Input is 0, 0, 0. If g outputs 1, we will say it does not preserve 0 and the first property will be satisfied. But if on input 0, 0, 0, it outputs a 0, we will say it preserves 0 and the first property is not satisfied. So you can see this one will be 0. Here you have y. So this will be 0. Both of them are not complemented. So this one will also be 0. That means the output of this function is 0 on the input 0, 0, 0. So it preserves 0. Okay. But what we want is it must not preserve 0. So G fails this first property. That means G is not functionally complete. So with just substituting 0, 0, 0, we can declare that G is not functionally complete. Okay. That means you need not check these 4 properties for this function G. Just if any one property fails, you can declare it is not functionally complete. Okay. Now let's move on to second property. Second property says it must not preserve 1. What is the meaning of it must not preserve 1? Now we need not care about this function g, leave it. It must not preserve 1 means if input is all ones, the output must not be 1. Okay, if the output is not 1, we will say it does not preserves 1. Okay, let's check it for f. All ones means you will get a 0 here because x bar, 1 bar is 0. So this term will become 0. This will also become 0 and this is obviously 0. That means output of function f on all ones is 0. Okay. So from here you can declare it preserves, it does not preserve 0. From here you can declare it does not preserve 1. So function f satisfies property 2 also. Okay. Third property says it must not be linear. What is the meaning of a linear function? Now first point is you need to have the entire truth table for checking if the function is linear or not. Okay. Rather, for all these three properties, you need to know the truth table. So let us fill the truth table first. I'll do it for you. Okay, so I've filled the truth table. There's one shortcut to fill it. See, analyze all these three terms one by one. Y bar Z bar will output a 1 when values of Y and Z are both 0 zeros. Okay, so when values of Y and Z are both 0 zeros, Y bar Z bar will become 1. Okay, so entire function will be 1. So where are the values of Y and Z 0 0? 1 this case and 1 this case. So both of them will output a 1. Okay. Similarly, x and y have to have values of 1 and 0 to output a 1. In case of x is equal to 1, y is equal to 0, you can see x y bar will become 1 and this entire function will output 1. So x is equal to 1, y is equal to 0 is here as well as here. So both of them will be 1. Similarly, you can analyze the first term, this one also. It is 0, 1, 1. At input 0, 1, 1, the function's value will be 1. Okay. So we have filled this table. Now let's analyze this third property for the function f. It says function must not be linear. What is the meaning of linear? For a function to be linear, on all the places where it outputs high, output is high here, here, here as well as here. On all these places, number of inputs that are high must be either even or odd. Okay, let me repeat. On all these places, here, here, here as well as here, the number of inputs that are high, that means number of ones in input, must be either odd or even at all the places. Here you can see the number of inputs that are high are 0. So 0 is even. Here we are having even number of inputs that are high. Here we are having even number of inputs that are high. Okay. This is 2, this is also. There are 2 inputs that are high, 2 is even. Here you are having odd number of inputs that are high. That means our property failed here. Okay, so this function is not linear. Okay, had all of these been even, there's another point to linear also, we'll discuss it right now. But for now, you know that this has failed. Okay, so function f is not linear. Because this property failed, we can declare it as not linear. Okay, and that is what is required. Function must not be linear. So f passes this property. Now, just allow me to discuss this property of function being linear for 1 more minute. First point says, wherever output is 1, the number of inputs that are 1 must be either even or odd. If all of them are even, if all the places where output is 1, number of inputs that are even. In that case, in these places where the output is 0, the number of inputs that are high must be odd. Okay. The second case is when all these places have odd number of inputs that are high. That means wherever function outputs 1, in those places the number of inputs that are 1 are odd. Okay. Here also odd, here also odd, here also odd, and here also odd. In that case, these places must have even number of inputs that are high. Okay. That means first point says all of them must be either even or odd. Second point says at these places you need the opposite. If it was odd, then you need even. If it was even, then you need odd. I hope you understood it. Else I'll just link some PDF in the description. You can read it from there. I've also discussed it in a great detail in my theory lectures. So let's move on to the next point. Function must not be monotone. What is the meaning of monotone? Instead of proving that it is a monotone, it's easier to prove that it is not a monotone. How can we prove it? Let me raise the board. For this fourth property, if you select some input, that means say this one, 0, 1, 0, and you turn any input on. For turning an input on, first of all you select an input that is off. Now both X and Z are already off. You turn them on. That means if you make any one of these on, from 0, 1, 0, you will reach to 1, 1, 0. That means here. Okay. From here you reached here. What you essentially did was you just made this 0, 1. In this case, if the output of functions changes from 1 to 0, you can declare this function as not monotone. Okay. Let us find such case. Yeah, it's available here. See, you changed z from 0 to 1, but output changes from 1 to 0. So this function is not monotone. Okay. F passes this property. It is not a monotone. Last point is it must not be self-dual. For declaring a function self-dual, there are 2 points again. Linear also had 2 points. Okay. Here also you need to prove 2 points. So if you want to prove a function is self-dual, okay, what needs to be done? First point is it must have same number of minterms and maxterms. If the function fails here, if the number of minterms as well as maxterms are different, we can simply declare it is not a self-dual function and this question will be done. But here you can see you have 3 plus 1, 4 minterms, these 4, wherever the function outputs 1, as well as you have 4 max terms. Okay, 4 minterms and 4 max terms. That means there is a possibility that this function could be self-dual. Okay, so let's go for the second point. What is second point saying? Second point says you make these pairs. So you can see I've made groups of mutually exclusive terms. They are 0 and 7, 1 and 6, 2 and 5, so on. Okay. Any one of this pair could have a value 1, other has to have a value 0. Okay. You can see out of this pair, this one, we have one value 0 and other value, one value is 1, other value is 0. It's okay. This is accepted. From here, one of them is 0 and other one is also 0. This is not accepted. Okay, so this function is not self-dual. It fails here. This function is not self-dual and hence you can simply declare that f is functionally complete. because the fifth property is also satisfied. F satisfies all the properties, so function F is functionally complete. Okay. Now there is one more method. This one. Let's discuss this one also. You can see this function g could be minimized. So function g will contain, just take x bar y common from here. This will become x bar y plus xy. Apply absorption law here and you will get y. Okay. This function g could be minimized to y. Function g becomes y. That means in no case it can derive NOT gate. Okay. Whatever be the inputs, you cannot derive NOT gate. And both of these need NOT gate. So g can never be functionally complete. Let's discuss about this function f now. So you can see absorption law is not applicable, nothing is common. So let's try to manipulate the inputs such that we are able to derive NOT gate from here. So three variables are present in complement form, that is x here, y here and z here. Let's do one thing. Let's try to eliminate both of these terms by substituting y is equal to 1. Okay. This term will vanish. This term will also vanish, because when y is equal to 1, y complement will be 0. So this term will become 0 and this term will also become 0. Also, when y is equal to 1, we have substituted y is equal to 1. You will get x bar z. Now we want only x bar. Okay. Z must vanish from here. For that you need to substitute z is equal to 1. Okay. Because when z becomes 1, these two are already gone. If z is 1, y is 1, both of them will be 1 and 1 and we will be left with x bar. Okay. So the input is x1, 1. In this input, the output of the function will be x bar. Let me write it. F of x comma 1, 1 is equal to x bar. So we have derived NOT gate from function f. Now let's try to derive either AND or. Which one? Let's see which one is easy. You can see on this input x and y is equal to 1. We got, these two will vanish. We got x bar z on the input. X comma 1 comma z. The output is x bar z. Okay. But we want xz. Okay. These we want AND of any two terms. AND will be xz. Now we already have derived NOT gate from here. That means we can complement any input. So what you do? You input x bar. The output will become xz. Okay. So on this input, we have got x bar. On this input, we have got AND. So NOT and AND could be derived using this function f. That means NAND can be implemented from f. So this function is functionally complete and g is not functionally complete. Your answer is f is functionally complete, g is not functionally complete. Okay.